this. So as an overview, salt dome production in Houston and Beaumont really catapulted Texas as one of the United States leading oil producers from 1901 to 1960s. But today, 123 years later, it's a totally different story. I mean, these onshore salt exploration really became extinct right around the 1990s. The whole industry, including my career, everyone went offshore to offshore Texas, offshore Louisiana, and these domes really just stopped being drilled for exploration. There are still replacement wells being drilled. There's a few development wells, but very, very few what I would call exploratory wells. We're going to look at reservoir trap and salt morphology, and we're going to talk a little bit how seismic processing could really reinvigorate these domes, because as you've known and you've seen other talks in the conference, there's been vast improvements in seismic migration that I think would really make a difference in exploring these domes. So here's our base map. This green area is the greater Houston area, maybe all some from Houston. We're going to talk about Humble Dome, Pierce Junction, we're talking about Spindletop and Barbers Hill, and we'll talk about Damon Mound, and then Hockley Dome. So if you're familiar with the Houston area, you may not have realized that these salt domes are really within the 610-99 loop. Some of them are surface expressions, some of them are below the city has covered them. And I found this very, very interesting that you live so close to salt domes and you don't really know. So let's talk a little bit. I had in the 4 or 5 county area, I made a Kingdom project, a SMT project, and there were 100,000 wells in my project when I got them from the S&P group. And so there are 33 salt domes. I decided to just sample them to Humble and these names right in here. And I'd like to get back and study all of them. It was just sort of a time limitation. Each one of these domes has something unique about it. And we're going to talk a little bit about the most productive ones are Humble, Spindletop, Barbers Hill, Pierce Junction. And then one thing I want to call your attention to is how the production just drops off. I mean, it's very, very bimodal. Webster and Thompson are really salt cord anticlines, and they're at the 500 million barrel range. You have Humble, which is nearly 200 million barrels. And then as you go down, I mean, look how it just drops off. And my question was, why are they not all even? Why are some like barely productive at all? And why is Humble and Spindletop 200 million barrels? And the goal of my presentation was to show you there's about 5 criteria you have to have.
So many people will be surprised to learn that salt dome aerial size is not correlated with total production in the study area. For example, you see Bowling Dome here at the upper left, which is 33 million barrels, but it's a huge dome, over 9,000 acres aerially. And Humble is also a very large dome and very productive, but there are many domes of similar size that have vastly different production. For example, Hockley and Barbers Hill are pretty close to the same size aerially, but Barbers Hill produces 135 million barrels and Hockley produces 1. And one of the smallest domes is Spindletop, which has produced 151 million barrels. So salt dome aerial size is not correlated with total production. Here's a location map of the Houston area salt dome study, and we see the Wilcox trend in the north. So the Frio, Vicksburg, and Yewa are on the sides of the dome for Humble Dome and Hockley Dome. As you go down to the coast, the domes are then surrounded by the Frio trend, which includes Pierce Junction and Barbers Hill. And as we proceed down the coast, the Frio trend goes deeper, and now we have the Miocene trend covering the tops of the dome and also being on the sides of the dome, which includes the Damon Mound and Bowling Dome and Spindletop as well. Let's take a look at this graph of the early history of exploration of Houston and Beaumont, and you'll see that many of the domes in the study were discovered between 1900 and 1903 or 05. You'll see Barbers Hill. Spindletop was the first one in January 1900, but Barbers Hill, Damon Mound, Pierce Junction, all these are surface expressions. Then the industry took a break for World War I, and they've started finding more domes in the Houston area using the gravity torsion balance method, in addition to surface topography. And later on, even in the 30s, became the first seismic data. So the last dome discovered in the Houston area was actually Webster in 1934. Let's take a look at case study number 1, the Humble Salt Dome in Harris County. You'll see the green area is the Houston area, and Humble is in the northwest near the IAH airport. So here we see an air photo where you'll see the Houston Airport, IAH, on I-69, and just a few miles to the west is the Humble Salt Dome. You see a Frio structural map that shows that the Frio is on the sides of the dome, and this cross-section, which goes from the northwest to the southeast, shows a pretty good strat column of what's in this area, including, there are Miocene sands up against the dome, there's a sandy Frio-Vicksburg section, a sandy Yewa section, and even the Wilcox has been penetrated on the northwest side and produces gas. Let's take a look at the Humble Salt Dome in this view demonstration. So we see that the Humble Salt Dome looks like a pincushion covered with over 2,500 wells drilled. There are 1,612 productive wells, and this type log off to the right shows the Frio deltaic sands. You'll see that they coarsen upward and they're often full to spill, or they have a boxcar presentation showing that these are marginal marine sands.
The top of Frio map, and one of the things that contributes to Humble's success, of course, is its size, but it's just totally in a rim syncline all around the dome. And one thing you can also see is that when you look at the closures on the production at the Frio level, it's about 750 feet tall off of regional. So it's, as you saw in the visualization, it's a very tall dome off of regional. It has closures on, it has a big overhang here on the northwest side where some of the sands can park in and get trapped up here on the northwest side. But generally all sides of the dome are productive in some way. So we have stacked pays, an overhang, we have a rim syncline all around it. And then another feature is, if you go into Halbedy's book, they publish that there's kind of a shatter pattern across the top of the dome. So here's my cross section that goes from the northwest to the southeast, and a nice sort of a strat column for the whole Houston area is there sands in the Miocene, you have a Frio Oligocene package, a Shaley Vicksburg package, Yewa, and then Eocene, and then you have a little bit of Wilcox at depth. So this depicts the the production here on the southeast side. You can see all the wells coming up against the dome. And so we have stacked pays, and I also want to call your attention to the thinning beds. So this is a dome that's rising with time gradually, and it's pulling the beds up, which really accentuates its ability to trap oil and gas. So we're going to see porous reservoir sands, stacked pays, thinning beds. And in this particular dome, a very, very straight wall down. So now here's our case study number 2. Everyone's alluding to the famous Spindletop. So here's Houston, here's Barbers Hill, and so Spindletop is in Jefferson County off to the east. You may have read the book Giant Under the Hill. If you want the backstory about the human experience, go get this book called Giant Under the Hill. So I made the little salt dome raise up under here. This is not a very big dome aerially. It's only 737 acres. One of the first domes discovered. Today it produced 151 million barrels. It's still actively being drilled today. So the discoverer was wildcatter Patia Higgins. He found it as a surface expression that he could light the gas on fire. But let's take a more modern look about its mapping at the Frio level where it produces. Again, this is an extremely tall structure off of regional. If you look at the bottom closing and the top closing contours at the Frio, it's over 900 feet tall. So again, one of the secrets of success of highly productive domes is they're very tall off of regional. And then here I have a little view pack rendition where you see the top assault and the Frio map. And in this case, I'm only displaying, there's a famous overhang that was discovered in 1925 on the southwest side. And I think the whole dome, it tends to lean to the south as you see this depression in the Frio. I get the whole sense the whole dome is leaning to the south, but I've got a seismic line, so you'll be able to look for yourself. So here's my top assault map on top of an older map. Here's where the overhang is. And one of the big things that makes Spindletop so productive is stacked pays. Each well could have 3, 5, 7 feet of pay in the same well. So that's how it packs a lot of production to a small amount of place. It has abundant Frio pays and Miocene pays, and some of the pays are 50 feet thick, 100 feet thick. I mean, if you've drilled for oil and gas, getting that size of pays is tremendously productive and adds to the whole cumulative production. But they are deltaic sands and they're very porous. So here's my first Spindletop cross-section, and this tells you a lot. Again, you see the thinning beds onto the dome. This is where the southwest overhang is. I mean, I didn't depict these wells going under the overhang, but they actually, there's enough of the salt rolls out over the top of the formation that a lot of the pays are underneath the salt, which makes it a great trap. It also has some Miocene production, and it's less productive on the north side, but it does have a little bit of production. And the famous cap rock is Miocene in age, and that's where they had the blowout in 1901. They did get 1 million barrels out of the top of the dome, but they got far more millions of barrels on the southeast side. So it's, again, rises high over regional dip. It's abundant porous sands, stacked pays. One of the limitations of Spindletop is that there seems to be a very shaly section below the Frio, at least on this side. So these digital wells show you that they have kind of abandoned exploration on the deep side because it seems to be so shaly. So here, my friend Robert Pledger, who has actual acreage and is a producer at Spindletop, said it was okay with him to share this seismic line. This is a time migrated, it's not pre-stacked time or pre-stacked depth, it's a time migrated volume that he uses from the 80s. And here's the overhang on the south side. So I'm sure you're all mentally like drawing in your dome here. One of the features of time data is you get what are called a migration shadow. So, we see some great examples in processing in our other talks where they're able to collapse in the reflectors and, maybe there's a stock there. I mean, your eye is as good as my eye, but we know that there actually are beds underneath here. So here's my interpretation. I put in the horizons that produce at Spindletop, and this log kind of fits in along here where you see one of the elements is the stacked pays, and then here's a dome interpretation. So I don't see it as a roofless dome, but someone told me at the conference there's even a better 3D over Spindletop. And so, but I do get the sense that the whole dome is leaning toward its overhang on the south side. So Z-Terra is a processing company really near us in Katy, and this is offshore, but this looks a lot like what I think would happen if you were reprocessing the seismic over these onshore domes. Here you see the classic migration shadow because they can't migrate the events, whereas if Z-Terra or another company was able to use wave equation migration or this beam modeling they do, they can get the reflectors much more identifiable on the sides of the dome. And so one of the benefits this would be is if you had seismic over these old domes, you might be able to find another overhang, which would be worth millions of barrels. So my case study number 3 is Barber's Hill. So we looked at Humble, and now we're going to look at Barber's Hill. So Barber's Hill is not a very big dome, but it is one of the most productive domes per acre. And one of its features, just like you saw at Humble, is it has a rim syncline around it. And it also stands up very high against regional dip, but it's not very large. It produces from the Frio, and it has a very prominent overhang. The overhangs are not always on the same side. As you noted, the Spindletop's on the southwest, Humble was on the northwest, this one's on the northeast. So the overhangs are not on the same side, but they may have something to do with the orientation of the dome stock. So here's a map at the Frio, and you can see that Barbers Hill has quite a few amounts of wells on the east side. That's its most productive side, and it produces out of the Frio. They also have some production up here on the northwest side. So I sort of flattened the Frio cross section, and again, what do you see? Multiple stacked pays. So note how you build a huge amount of cumulative production in these domes. It's not related to the size of the dome. It's related to how tall it is off regional, and also how many stacked pays you have. So one cross section is, here you see a digital log where you see the Miocene and the Frio pays on the west side, but the most productive side is the salt overhang on the east side. So I put some symbols down so you can see the thinning beds going up on Barbers Hill, and you can see that it has the multiple stacked pays. So here's a classic cross section from the literature where they were trying to delineate the overhang using well control. Here's what it looks like on my workstation, approximately in the same direction. And of course, this goes from the southwest to the northeast. And there's a Frio structure map. We're going to look at our last highly productive dome is called Pierce Junction. Now, Pierce Junction is a pretty classic dome. It's not about the same size as Barbers Hill, but it has sort of a history story to it. So this man is called Hugh Roy Cullen. He's a famous wildcatter. He originally entered the business as a cotton trader and decided he heard all his friends were making money in the oil business. So his first investment was actually Humble Dome. But he was very, very shrewd man. I believe he understood enough geology by just a simulation and trying to figure out what's going on that he realized that he learned from Humble Dome that if you drill off to the side of the dome, you can find a lot of pay. So he had to convince his investors that originally the Pierce Junction field was a bunch of dry holes on the top of the dome. And so he had to convince his investors, without any seismic or any other wells, to drill down dip of dry holes. And of course, it took him several years and many dry holes, but boy did he hit the big one on the east side of Pierce Junction field. And I recommend the book called The Big Rich. It's by Brian Burroughs, who has a very colorful chapter about Hugh Roy Cullen. Also, Cullen, after he became pretty wealthy, contributed to the University of Houston with the Cullen Engineering Center and also the Museum of Natural Science and many, many other things. So here's a Pierce Junction cross section from the west to the east. And this is what he found when he eventually delineated the east side of the wells by drilling. It's an overhang with a very steeply dipping beds up against the salt and multiple pays. So you have the salt overhang on the east side, thinning beds on the dome. You have variable thickness of reservoir, but you have multiple stacked pays. And that's how you put a lot of hydrocarbons in a relatively small space. And now here's the top of salt. You can see today all the wells that penetrate the top of salt that go in and get that overhang. And there's an example of the logs. The beds are Miocene, they're deltaic, they coarsen upward, or they're boxcar sands. Let's take a look at a low productive dome. With all you've learned from this talk, we're going to take a look at Hockley Dome. So Pierce Junction is 92 million barrels, and Humble's 168 million barrels, but Hockley barely produces anything. So near my house, we go up to Hockley Dome because there's a bird watching platform up there. So when you get on top of the bird watching platform and you look down to the south toward the salt mine, you can barely see a little bit of a hill. But the hill was visible to Petit O'Higgins was out here in 1901. He was drilling some of the first wells on Hockley Dome. So here's the Katy Prairie Conservancy. The dome is not under the Conservancy. It's on private land over Warren Lake. But one of the features, it produces from the Frio on the southwest side and also from the northeast side, but the sands are quite a bit thinner at Hockley Dome. So one of the things that's falling away from the model is it doesn't have thick sands. Now, if you take a look at some structure maps that I made, and you subtract the deeper Frio horizons from the top, you're really only getting about 350 feet of closure. So instead of 700 feet of closure or 900 feet of closure, you don't have a lot of relief on the Hockley Dome. So here it is in a visualization model, and we're going to take a look at a cross section from A to A prime. So here you see it's got sand. I mean, some of the pays are thin, but it has abundant sand on the southwest side. It has sand on the northwest side. It's not a lack of reservoir. It's shaped quite a bit like all the other domes. It has a cap rock, and as you probably know, it has a salt mine under the cap rock. And there's Miocene and Frio all around the dome, and there has not been a lot of deep drilling at the Hockley. So mostly the wells stop around 7,000 feet in the Frio. But what's the problem with Hockley Dome? Well, if you make a regional map on the Frio, you can see that, I told you that there wasn't a tall closure around Hockley, but when you put that on a regional map, there's abundant places that the hydrocarbons can bypass Hockley. And even Halbudi mentioned in his book that he thought perhaps some of the hydrocarbons that didn't accumulate at Hockley went into the Katy gas field, which is a TCF gas field in the Yewa and the Wilcox. And then there's some other small closures over here, and I think it also has the potential to vent up to the north. Another low-producing dome is San Felipe Dome, and I think it has the same problem. I think you have regional migration away from the dome and kind of the inability to preserve hydrocarbons that are migrating toward it. So here's two domes. One is very productive at 135 million barrels at Barber's Hill. It's got the overhang. Here, Hockley Dome has an overhang, but it's not quite as big. But see how you have thinning of the dome, thinning of the beds here, and you do not have thinning of the beds at Hockley Dome? So both domes have Miocene production in reservoir sands. Both domes have salt overhangs. Both domes have the same cap rock, and both domes have 120 years of exploration. But the difference at Hockley is it lacks the thinning. It has small trap closures up against the salt. And when you do regional maps, I see leak points where the hydrocarbons can go and leave the dome. And so therefore, none of these wells that produce at Hockley have a lot of stacked pays. If you want to look at another low productive dome, you can drive down to Damon Mound, and this is a really fun field trip, and you can continue on and see West Columbia Salt Dome, which is very productive. So here's Damon Mound from the road, and it's a tall and small mound. It's only produced 11 million barrels, almost totally from Frio sands around the ring at the top of the dome. But it's a very nice site to take a picture of, because what makes it stand up off the road is the Frio has a limestone on top of it. So you're seeing like a limestone mound, and then there's a salt dome underneath it. So in Google Earth, it allows you to do the elevation profile. If you drive down the road here and take a look to the east, you'll be at 60 feet. It's really an 82-foot mound with a salt dome under it. So the conclusions for my talk are, the lessons you learn from highly productive domes is you need to have all of these to be a highly productive dome. It's not just 2 out of 3 or 4 out of 5 or whatever. You got to have all of these. You have to have the Miocene and Frio, and even the Yewa and Wilcox are very good reservoir. You have to have stacked pays, because the multiple pays really add up the production. You have to have thinning beds. So the dome has to be a timely dome that's rising with the deposition of the Miocene, Frio, and Yewa, and the beds are thinning on the dome, because that creates the strongest traps. And then you need to have a dome that is very prominent against regional dip with the rim syncline on it, and salt overhangs add quite a bit of reserves to these domes. So the lessons we learned from the less productive domes is that even though you can have reservoir, if you have thin PEDs, it's going to cut down, thin pays, it's going to cut down your reserves. The thinning beds are very important. So any dome like Hockley that seems like the beds are just the same thickness on either side, that's not a good sign. And you need always to look at regional mapping because, you know, if you were going to study a salt dome, most people would just draw a little box around the dome and they go and get all the logs and they'd have a lot of work to do. But if you don't integrate the regional, you don't know if there's leak points around the dome that could take away the reserves. And then you need a small salt dome with small overhangs is very bad for cumulative production. So the future work that I recommend is that we go the seismic route on the onshore salt domes and either reprocess existing seismic or get new seismic, because in this Z-Terra model, you know, just finding a salt overhang on one of the older domes could add millions of barrels to what they think is an extinct play. And I think that there's a future in looking back at the onshore domes. So thank you very much.